Welcome to Center of Math's Advanced Knowledge Problem of the Week. For this week's problem, we want to prove that every compact metric space has a countable base. So to do this, we're going to construct our base by taking covers. So we're going to take all our points in our metric space. We're going to have a ball of radius 1 over n. We're going to have a finite subcover of that cover. And we're going to take the union of all these finite subcovers to get a countable base. And we just need to prove that this, in fact, is a base. So for each x in our metric space, call it M, we're going to take an open set x, 1 over n, so an open ball around x, or radius 1 over n. So yeah, this is just an open ball, and we do that around each point, but since the metric space is compact, we must have a finite subcover. We're going to call that subcover S1 over n. And then we want to prove that so we want to prove the set of all open balls of the union from n equals 1 to infinity of S1 over n is a base for our compact metric space. So this is the countable union of a bunch of finite sets. So this itself is countable, and we just want to prove that it's a base, and that will be our countable base. So to prove that our base is in fact a base, and it's a set of a bunch of open sets, we want to prove that for any arbitrary open set in our compact metric space, we can take a union of our base and get that open set. And it's sufficient to prove that for any open set, we take a point, and we can find an open set from our base that contains that point and is contained in the open set. Then we just take a union of all our points in the respective open sets that contain each point, and we'll get our open set. So to do this, take some arbitrary open set U in our metric space M, take X, say it's a member of U, and now say X, so since it's open, we must be able to find an open ball around X that's contained in the open set. So X is a member of, say, P, where P is some open ball contained in our open set U. So now, so for every set of balls of radius 1 over n, we can always find, so they cover our set. So each x must be a member of at least one of the balls for each of these sets. Now we're going to pick 1 over n, so that it's less than or equal to r over 2, where r is the radius of this ball P with center little p, or with center x. Now, so x is going to be a member of some L of the sets of radius 1 over n, where 1 over n is less than or equal to r over 2. Now say y is also contained in this open ball of x. So if y is a member of L, we want to look at the distance between x and y, so that's less than or equal to, we're going to say L has center little l, so that's less than or equal to the distance little l x plus distance little l y by the triangle inequality. For each of these, since L is the center of an open ball of radius less than or equal to r over 2, these are each less than or equal to r over 2. So this sum must be less than or equal to r. And so the distance between x and y must be less than or equal to r. This implies that y is in fact contained in the open ball of radius r, of which x is the center of. So yeah, so this implies y is a member of P, and so L is in fact contained in P, which is contained in U. And x is contained in L, so we found member L of our base, which has an open ball which contains x and is contained in an arbitrary open set. And so that proves that our countable union of all these sets must in fact be a base. Thanks for watching. Please check out centerofmath.org and follow us on Facebook and Twitter. Thank you.